Welcome you all in this lecture on E-H-plane T-junction or hybrid or magic T-junction. So in the previous two lectures we have discussed E-plane T-junction and H-plane T-junction. But in this lecture we will discuss a hybrid T-junction, which is basically a combination of both E-plane T-junction and an H-plane T-junction. As can be seen from figure 1, ports 1, 2, 3 correspond to an H-plane T-junction. So the arms corresponding to port 1, 2 and 3, they correspond to an H-plane T-junction, whereas the arms, for example, the arms 1, 2 and 4, they correspond to an E-plane T-junction. So a combination of both H-plane and E-plane T-junction forms an E-H-plane T-junction, which is also called as a hybrid or magic T-junction. Figure 2 shows the physical structure of a magic T, and the ports 1, 2, 3 and 4 are as shown. So these ports 1 and 2 are collinear, as can be seen. Port 3 here, port 3 is in the H arm, so this port is in the H arm. And port 4 so far is concerned, it is in the E arm. This is E arm. So it is formed basically by cutting slots along both the breadth and width of the main waveguide. Say for example, we have this as our rectangular waveguide. Let me draw it. This is our rectangular waveguide. And this is the cross section. So as we know, in case of an H-plane T-junction, what we used to do was that we used to cut a slot here along the width. In case of an H-plane T-junction, we use to cut this slot and attach another section of a waveguide. For example, on cutting this slot, we'll attach a waveguide section along this width, and this used to be our H arm. So till now this is an H-plane. This looks like an H-plane T-junction. Now for making it a hybrid junction, what we use to do, or what we do, is that we cut a slot along the broader dimension here. We cut another slot along this broader dimension. On cutting this slot, we attach another section of a waveguide. And the section of a waveguide. This corresponds to the E arm, as in case of an E-plane T-junction. This corresponds to H arm. So we have ports 1, 2 are collinear, port 3 is in the H arm, and port 4 is in the E arm. So this is what a magic T looks like, and this is how it is being formed. So the need for this 4-port junction arises from the fact that there's a basic limitation with 3-port junctions. 3-port junctions like E-plane T and H-plane T. The limitation basically is that it is impossible to construct a 3-port lossless reciprocal network that is matched at all the three ports. So we cannot have a lossless reciprocal network matched at all the three ports. All it means is that we cannot have a three-port network wherein we have S110, S220, S330. We cannot have simultaneously these three parameters as zero. This is one of the limitations with the three-port networks. Say for example, as we know, in case of an E-plane T junction which is a three-port junction, or an H-plane T junction which again is a three-port junction, the S matrix would be something like S11, S12, S13, S21, S22, S23, S31, S32, S33. So the problem is that we cannot have this S11, these diagonal elements. We cannot have these diagonal elements. We cannot have all of these diagonal elements equal to 0. So instead, we have a four-port junction, which is basically lossless, reciprocal, matched at all the four ports, like our EH plane T junction. EH plane junction, also called as hybrid junction or a magic T or a hybrid T. So this four-port junction, as we'll be discussing this four-port junction, EH plane T, or you can look at this figure as well, this has the property that it is matched at all the four ports. What that means is that S11 is 0, S22 is 0, S33 is 0, S44 is 0. All the diagonal elements in the S matrix of this four-port network would be 0. Further, as I said, this hybrid junction basically, or this magic T, is basically a combination of E and H plane junctions. So it has the properties, the power splitting and combining properties, both of E and H plane T's. So let me write it somewhere. This four-port junction, hybrid T or magic T, has the power dividing / combining properties of both H-plane T and E-plane T junctions. So the advantage is that this four-port junction retains the properties of both E and H-plane T junctions. Now the various properties of this E and H-plane T junction, the hybrid T junction, can be understood from properties. As I said, properties can be understood from its S matrix. Now, since there are four ports in a magic T or in a hybrid T, in a magic T, so the S matrix must be of order 4 cross 4, order of S matrix. So that means our S matrix should look like S11, S12, S13, S14, S21, S22, S23, S21, 22, 23, 24, S31, S32, S33, S34, S41, S42, S43, and finally S44. This is our S matrix. Now point number 2. As I said, this hybrid junction retains the properties of E and H plane T junctions. Now looking at this junction again, we know from H plane T junction S13 or S23, S23 is same as S13. This is what we have seen. 2, 3 is same as 1, 3 because of the symmetry. S23 is same as S13. So I can write here because of H plane T section, S23 is same as S13. Now again, let me copy the figure here, paste. See, I said S23, S23 is same as S13. Now because of this, this is our port 1, 2, 3, and this is our port 4. Now because of E plane, we have again E plane T section. This corresponding to the E arm. Because of E plane T section, we have S24, S2, let me use this color. S24 is same as S14 in magnitude, but they are out of phase. Magnitude is same, but they are out of phase, as has been already shown in the previous lecture. S24 is same as that of S14, but the only thing is that we have to place a minus sign because they are out of phase. So S24 is same as minus times S14. We can write fourth point as well. Fourth point will be, so far as ports 3 and 4 are concerned, so far as ports 3 and 4, this is port number 4 and this is port number 3. So far as these two ports are concerned, they are isolated. Ports 3 and 4 are isolated. They are isolated. What that means is that if we connect a source here at port 3, no energy will come out of port 4. Or for that matter, if we are connecting a signal at port 4, we won't receive any power at port 3. So ports 3 and 4 are isolated. So in terms of S parameters, that means S34 is same as S43, and since they are isolated, they are equal to 0. And again, from symmetry property, we know Sij has to be same as Sji. So what that means is S12 would be same as S21, S13 would be same as S31, S23 would be same as S32, S34 would be same as S43, S24 would be same as S42, Sij in general is equal to Sji. Likewise, S41 has to be same as S14. And again, we have seen from E and H plane T's, we have seen there in case of an H plane T junction, ports 1, 2, and 3, as I said, they correspond to H plane T. So as we have seen that there in case of an H plane T junction, port 3 is perfectly matched to the junction. and there we said S33 is equal to 0. And again, in case of an E-plane T junction, would mean the arms corresponding to this arms corresponding to ports 1, ports 2, and ports 4. Again, we said there that this E-arm junction, that is the port 4 here, is also matched to the junction. That means S44 is 0. So this is what we have seen. In case of an H-plane T junction, the side arm port is matched, and in case of an E-plane T junction, the port that is attached to the side arm, here the E arm, is matched to the junction. That means S44 is 0. So I'll write it as ports 3 and 4, ports 3 and 4 are perfectly matched to the junction. Are perfectly matched to the junction. That means S33 is same as S44 is equal to 0. So therefore our S matrix becomes S11, S12, S13 on using these above properties, S13, S14, S12, because S21 is same as S12, S22 is there, S13 is same as S31 minus times S14. This is S13, this is S13, this is 0, and this is 0. S14, this is minus times S14, this is 0, this is 0. Now again, we know from unitary property, we know that S into S star is I. This is what we have already shown, that for lossless networks, S into S conjugate is a unit matrix. So if we use this on this S matrix, we'll obtain a set of equations, and from that set of equations, we'll be able to find these S parameters. Now, if we look at this, we have 1, 2, 3, 4, 5. We have around 5 unknowns. So we'll need to write sets of equations so that we can find these unknowns. So if I multiply row 1 and column 1, let me first write this S and S star, as I said, is I. So our S is this. This is our S. So let me rewrite it as S is S11, S12, S13, S14, S12, S22, S13, and then S14. Then we have S13, S13, 0, 0, S14, S14, 0, 0. Then its conjugate, S11 conjugate, the conjugate of these elements, S11, S12, etc. S12 conjugate, S13 conjugate, S14 conjugate, S12 conjugate, S22 conjugate, S13 conjugate, S14 conjugate, S13 conjugate, S13 conjugate, 0, 0, S14 conjugate, S14 conjugate, 0, 0. This has to be a unit matrix I. The order of I would be same as that of order of S. Since S is a 4 cross 4 matrix, so our unit matrix must be of the same order, 4 cross 4 matrix. So it's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, So this is our S matrix. Now if I multiply row 1 with column 1, if I multiply row 1 with column 1, I'll get the first diagonal element, which is 1. So S11 into S11 star would be simply S11 square, magnitude square. Likewise, S12 conjugate would simply be S12 square. Likewise, S13 square. And when I multiply S14 with S14 conjugate, I get S14 square. And on the right side, we have to equate it to this one. So let's name it as equation 1 first. Likewise, now if I multiply row 2, let me use a different color. If I multiply row 2 with column 2, we'll get the second diagonal element, which is also 1. So on multiplying row 2 with column 2, we get S12 square, S22 square, S22 square, S13 square, S13 square plus S14 square is equal to 1. Let's name it as equation 2nd. Likewise, if I multiply row 3 with column 3, we'll get the third diagonal element here. So this would mean row 3 with column 3, S13 square plus S13 into S13 would be S13 square. S13 into S13 would be again S13 square, mod of S13 square. And on the right hand side we have a 1. Now on multiplying row 4 and column 4, row 4 and column 4, if we multiply row 4 with this column 4, we again get this diagonal element. So S14 square plus S14 square is equal to 1. Let's name this as equation 3. Let's name this as equation 4. So from equation 3, twice S13 is equal to 1. That implies S13 is 1 over root 2. And from equation 4, this is from equation 3, from equation 4, from this equation, 2 times S14 modulus square is equal to 1, which implies S14 is 1 upon root 2. Again, if we look at equations 1 and equations 2, on right hand side we have 1. So if the right hand sides are equal, the left hand sides of equations 1 and 2 must be equal. So comparing equations 1 and 2. On comparing them, we have right side 1, so left hand sides we have to compare their left hand sides. So their left hand sides must be equal. So I can write it as S11 square plus S12 square plus S13 square plus S14 square is equal to S12 square, this S12 square plus S22 square plus S13 square plus S14 square. Now S11, S12, see we have S12 here, we have S12 here, they cancel out. We have S13 here, S13 here, S13 here, so they cancel out. And we again have S14 here and S14 here, so they again cancel. All we are left with is S11 square has to be equal to S22 square, which implies that S11 is same as S22. Now if I substitute S13, S14 and S11 equal to S22 in this equation, in equation number 1, so we get using these values in equation 1. Equation 1 is S11 square plus S12 square. I can write as S11 square plus S12 square. S12, as we can see, S12 is same as S11. So I can again write S11 square plus, then I have S13 square plus S14 square. But S13 is 1 over root 2, S14 is 1 over root 2. So I can write as 1 over root 2 square plus 1 over root 2 square is equal to 1. This is from equation number 1. So this means 2 times S11 square plus 1 over 2 plus 1 over 2 is equal to 1, which means 2 times S11 square plus 1 is equal to 1. This 1 and 1 will cancel out. That would mean 2 times S11 square is equal to 0, or in other words, that means S11 is 0. But since we know from this equation S11 is same as S22, but since S11 is same as S22, that means S22 is also 0. So therefore our S matrix, which we have obtained in step number 6, from step number 6 we have seen our S matrix is this. So we can substitute S11, S11, S12, S13, S14, etc. these values in this step 6. So that means our S matrix becomes, so let me rewrite the final S matrix then. Our S matrix becomes 0, 0, 1 over root 2, 1 over root 2, because S13 is 1 over root 2, S14 is 1 over root 2. This is what we have shown. S13 is 1 over root 2, S14 is 1 over root 2. S21 is same as S12, which is 0. S22 we have seen that S22 is 0. And again this is 1 over root 2, this is minus 1 over root 2. This we have seen is S13 is same as S31, so it is 1 over root 2. This is again 1 over root 2. This is 0, this is 0. And the fourth element, fourth row first, S41, we have seen S41 is same as S14, and your S41 is 0, is 1 over root 2. So S41 is 1 over root 2, minus 1 over root 2, 0, 0. So this is our final S matrix. Now we know the reflected waves and incident waves. The reflected matrix is this B, then we have S, and this is the incident matrix. A corresponds to incident waves, B corresponds to reflected waves. We know B is SA. Now in matrix form, we can write it as B1, B2, B3, B4 is S matrix, which is 0, 0, 1 over root 2, 1 over root 2. 0, 0, 1 over root 2, 1 over root 2. 1 over root 2, 1 over root 2, 0, 0. This is 1 over root 2. This is minus 1 over root 2. This is 0. This is 0. And then we have another column matrix corresponding to the incident waves as A1, A2, A3, A4. Now in equation form, we can write it as B1 would be simply 0 into A1 is 0, 0 into A2 would be 0, 1 over root 2 into A3, 1 over root 2 A3, 1 over root 2 A4, 1 over root 2 A1 is 1 over root 2 into A2 is 0, 0 over root 2 A2 is 0, 0 over root 2 A3 is 0, 0 over root 2 A4 is 0, 0 over root 2 A4 is 0, 0 over root 2 A3 is 0, 0 over root 2 A4 is 0, 0 over root 2 A4 is 0, 0 over root 2 A3 is 0, 0 over root 2 A4 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 This is our B1. Our B2 would be 0 into A1, 0 into A1 would be 0, 0 into A2 would be 0, 1 over root 2 A3, 1 over root 2 A3, minus 1 over root 2 A4. Likewise, our B3 would be simply 1 over root 2 A1, 1 over root 2 A2. And our B4 would be 1 over root 2 A1 minus 1 over root 2 into A2. So I can write it as, this is simply 1 over root 2 A3 plus A4, 1 over root 2 A3 minus A4, 1 over root 2 A1 plus A2, 1 over root 2 A1 minus A2. So this is the set of equations that we have obtained. Now let's discuss special cases. Special cases. Our case number 1. Let me paste the figure here. Paste. So this is our port 1. This is our port 1. Let me use a blue color. This is our port 1. This is our port 2. This is our port 3. And this is our port 4. So the first case, if we assume that we are not connecting sources at ports 1, 2 and 4. We are connecting a source only at port 3. So we feed a signal at port 3. So that means A3 is non-zero. Rest A1 equal to A2 equal to A4. They are all 0. We are feeding a signal at port 3 and we are not feeding signals at ports 1, 2, ports 1, 2 and ports 4 and port 4. And as we know, the incident wave, say for example, is designated here as this one. Incident wave here is this one. This would be A1. Incident wave at port 4 would be A4. Incident wave at port 2 would be A2. This A1 is 0, A2 is 0 and A4 is 0. This is what I mean that we are not connecting any sources at ports 1, 2 and 4. But yes, we are connecting a source at port 3. So A3 is not equal to 0. So let's see what happens under these conditions. What's our B1 then? So B1 in this case would be, because A4 is 0, it would be simply A3 by root 2. And B2 in this case would be, since A3 is non-zero, A4 is 0, so it simply would be A3 by root 2. Now B3 so far is concerned, B3 would be A1 plus A2. A1 is 0, A2 is 0, so B3 is 0. Likewise, our B4 again would be A1 minus A2 would again be 0. So let's see what it means. It means that, if I use this red pen, so this is basically our reflected wave at port 1, this is B1. This is reflected wave at port 2, this is B2. This is reflected wave at port 4, this would be B4. This is reflected wave at port 3, this would be B3. All it means is that B3 is 0, B4 is 0. So what it means is that we don't receive any power at this arm, B4 is 0. So we don't receive any power at this port number 4. B3 is also 0. So if we are connecting a signal source, we are feeding a signal at port 3, there are no reflections coming back to the source. So that's what B3 equal to 0 means. So, but B1 is A3 by root 2 and B1, this has a value and this has a value. So this means when we feed a signal at port 3, some part of the signal moves to port 1 and some part of the power moves to port 2. In fact, the signal fed at port 3 gets equally divided between ports 1 and 2, which is basically the property of H-plane T. Now let us discuss second case. Case 2. Let me again paste that image here. This is our H-plane, this is our magic T. So this is our port 1, 2, 3, this is our port 4, port 1, port 2, port 3 and port 4. So let's assume that A4 is not equal to 0. Let me use a different color. A4 not equal to 0. So that means we are feeding a signal at port 4. A4 not equal to 0. A1 equal to A2 equal to A3 equal to 0. That means we are not connecting sources at ports 1, 2 and 3. This A1 is 0. This is A1 incident wave at port 1. A2 is this and A3 is this. They are all 0. A1, A2, but A4, this wave, A4 is not equal to 0. So let us substitute these values in this set of equations that we have. P1 is 1 over root 2. So when we substitute these values, A4 not equal to 0 and these 3 are 0, in these equations we obtain B1 is equal to A4 by root 2. B2 is minus times A4 by root 2. B3 is 0 and again B4 is 0. So what it means is that all it means is B4 is 0 means this wave B4 is 0. That means when I connect a source at port number 4, power flows towards the junction and no power comes back to this junction. That's what B4 equal to 0 means. B3 equal to 0 means this again doesn't receive anything. Port 3 doesn't receive anything. As I already said that ports 3 and 4 are isolated. That means if I connect a source at port 4, we don't receive anything at port 3, which holds true here as well. So B3 is equal to 0, B4 equal to 0. Now coming to B1 and B2. Now B1, yes, we receive something because it has a value A4 by root 2. B1 is non-zero. And B2, which is the power received by port 2, is again non-zero. It has a value minus times A4 by root 2. So only thing is that, again, this means when we connect a source, or when we feed a signal at port number 4, it gets divided between ports 1 and 2, as is shown by these values B1 and B2. It gets divided between ports 1 and 2, but the only difference is that the power received or the signals that are being received at ports 1 and 2, they are out of phase because of this minus sign. They are out of phase. So this is basically the property of an E-plane T junction. This is same as the property of E-plane T junction. Let's discuss another case. Case number 3. This is an important case. So let's assume in this case that A1 is not equal to 0, A2 is equal to A3 is equal to A4 is equal to 0. So all I mean is, let me paste that image again, paste. So all I mean is that since we have this as our 4-port junction, what we say is that we are feeding a signal here. Let me use this pen. We are feeding a signal at port 1, so A1 is not equal to 0. A2, A3, A4 are 0. So we are not connecting anything at ports 2, 3 and 4. We are not connecting sources at ports 2, 3 and 4. Only thing that we are doing is that we are feeding a signal at port 1. So what happens is that if we substitute this thing A2, A3, A4 equal to 0 in the set of equations that we have already obtained, this is the set of equations that we have obtained for the magic T. On substituting the values in these equations, we get what we get is b1 is equal to 0, b2 is equal to 0, b3 is a1 over root 2, and b4 is a1 over root 2. So what that means is b1 is 0. So we are not receiving anything here. This b1 is 0. We are not receiving. If we are connecting or if we are feeding a signal at port 1, nothing comes back to the port 1. So there are no reflections back to the port 1. So b1 is 0. Again, b2 is 0. b2 is 0 would mean that port 2 doesn't receive any power or any energy. b2 is 0. b3 is a1 over root 2. b3 receives something and it is a1 by root 2. a1 by root 2. b4 again receives some power. Port 4 receives some power, which is again a1 by root 2. So if a1 is the power, is the amplitude of the signal here, so it gets equally divided between ports 3 and ports 4. The power that is being fed at port 1 gets equally divided between ports 3 and ports 4, as can be seen from this thing. But b2 is 0 means nothing comes to port 2. So if we are feeding a signal at port 1, it doesn't reach port 2. Nothing reaches port 2. So which is surprising, because ports 1 and 2, they are collinear. Apparently it looks like that if we connect something at port 1, it should reach port 2 as well. But what happens is, what we have seen is that if we connect something at port 1, it doesn't reach port 2. Nothing reaches port 2, which is surprising, and that must be the reason that it is called as a magic tea. So in this case, ports 1 and 2, they are isolated. Ports 1 and 2 are isolated. So similarly, if we connect a source at port 2, if we feed a signal at port 2, it won't reach port 1. It will be divided between ports 3 and 4. So that's it. There are other special cases. Say for example, we can have another case 4, another special case 4, a3 equal to a4, a1 equal to a2 equal to 0. We can have another special case, for example, as an exercise for students, we can have another special case, a1 equal to a2, a3 equal to a4, not equal to 0, b1 is 0, whatever, you can obtain the values. I leave these two cases, case 4 and case 5, as an exercise for students. That's all we have for the day. Good day.